Okay, everyone, welcome to today's lesson. This is the last lesson for unit number 1, complex numbers. This still deals with de Moivre's theorem, but this time we're going to use it in a slightly different way. Now, there's a few things I'd like to point out. Let me just go to a blank screen here for now, because there's a few things I want to point out first when you're finding, for example, square roots, cube roots, fourth roots of any number. If you're finding the square root of a number like, well, any number, like 25, let me get my pen working. Square roots of a number such as 25, there are actually two of them, 5 and -5, because -5 times -5 also gives you 25. Every number has two square roots. Cube roots of any number, it doesn't matter what the number is, there are always 3 of them. Now they might all be real, or you might have a real and two imaginary roots, but there are always 3 cube roots. Fourth roots, there are always 4 of them. Okay, and you can see the pattern that's going on here. There are 4 of them. And so that's something you have to keep in mind now when you start finding square roots, cube roots, fourth roots, or any roots really of any kind of a complex number. You have to be aware of how many of them there actually are. And also, when it comes to equations, I'd like to point out that you've seen linear equations so far. That would be degree 1, because the biggest power is 1. A degree 1 equation has one solution, or if you want to think of it, that's also one root. Quadratic, which would be degree 2, that always has 2 roots, and you saw that back in Math 1700. You could have also something called a cubic. Oops, I'm out of space. You could have a cubic equation, that's degree 3. And a cubic equation always has 3 roots, and so on. If you had a 4th degree equation to solve a polynomial equation, that would have 4 roots, and so on. So a couple of those things I want you to keep in mind now as we use de Moivre's theorem to find roots. And here's what we do. We first of all, if you're finding the square root of a number, remember that a square root of x, you can write that as a power if you wanted to. You could write that as x to the power of 1 over 2. All right, so what you're doing is that you're changing it from a root to a power, and therefore you can use de Moivre's theorem. If you're finding the cube root of any number, well, you can also write that as a power, x to the power of 1 over 3. Fourth roots would be x to the power of 1 over 4, and so on. So here's what we do. Here's how we find roots using de Moivre's theorem. First of all, you have to make sure the number, again, is written in polar form. You write the number in polar form, as it says here. Here's all the steps, by the way, in case you want to find them in your notes. Express the root in fractional notation, like we did right here or right here. Use de Moivre's theorem to find one of the roots, and you just do that regularly. You'll see when we do some examples now. And depending on how many roots it has, then what you have to do is repeat de Moivre's theorem, but you add 360 to the angle, however many times you need to add it to find the other roots. Remember, if you're finding a square root, there will be 2 of them. If you're finding a cube root, there will be 3 of those, and so on. So let's look at these examples here now. These are on page 26 in your notes. So it says, use de Moivre's theorem to find the roots of each equation. Okay, well, the first one is not really an equation as such. It's just a number. It's a complex number. And remember, 2j is actually written in rectangular form, because you can think of that as 0 plus 2j. So your first step would be to write that in polar form. And it's one of the simple cases. You don't really need to use a calculation to find r or to find the angle, because just ask yourself this simple question. If you were to graph 0 plus 2j, where would it end up to? Where would it, like the number, where would the vector be pointing? Well, 0 means you don't go left or right, so 0 on the real axis, but 2j on the imaginary axis means that your vector is actually pointing directly upward, like so. It will have a length of 2, so that's your r, and the angle, remember, excuse me, is in standard position. That angle right there is 90 degrees. So really there's no calculations required here to change this 2j into polar form. It is just 2, and then your angle symbol, and then 90 degrees. So there's the number right there in polar form. So remember, this question says find the square roots of 2j. So we know there are going to be 2 of them. Here's how you calculate the first one. If you want to find the square root of 2j, that would be written as 2j to the power of 1/2. Remember, square root. We change that into the polar form, so that would be 2, angle symbol, 90 degrees to the power of 1/2. And using de Moivre's theorem now, the r in front, which is your 2, that actually does get raised to the power of 1/2. So that's the square root of 2. In fact, if you wanted to, you could even leave it as root 2. Angle symbol, you take 1/2 of 90. And so this will become 1.414, or if you want to call it root 2, you can. 1.41. Root 2 would actually be better. And 45 degrees. Now, there is the first square root. But remember, the original number was given to us in rectangular form. So you would have to change this back into rectangular form using a equals r times the cosine of theta, and b is equal to r times the sine of theta. And if you do so, here is what you're going to get back. It's going to be 1.100 plus 1.00j. Now there it is in rectangular form. Now if you left it as root 2, if you left your r as root 2, that actually becomes exactly 1 plus j. That's what it really is. That's what it really is. Now, if you wanted to use your calculator to check that, to make sure it's really the square root of 2j, what you would do is take your calculator and square this. 1 plus, your calculator doesn't use j's, by the way. Your calculator uses I. So if you take 1 plus I and square it, you know what you're going to get? 2i. And that proves that 1 plus I, or 1 plus j in our case, is actually the square root of 2j. But now remember, that's only the first one. So here's how you calculate the second one. You take the original number before you took its square root, 2 times angle symbol 90. You add 360 degrees to the 90. But that's all. So your second root is going to become 2 angle symbol 450 to the power of 1/2. Oops, someone's at my door. Okay, so as I was saying, you add 360 to your 90 degrees to get 450. And now you apply de Moivre's theorem to this. So again, 2, which is your r, gets raised to the power of 1/2, which means root 2, square root of 2. You multiply 1/2 times 450. And you should end up with 1.41 or root 2. And now the angle this time becomes 225 degrees. So that's your answer in polar form. Now I'd like to point out, when you're doing questions like this, please read the question carefully. If the question had said, leave your answers in polar form, then this and this would have been sufficient. You would not have had to change it back into rectangular form. So please make sure you read the question carefully. Okay? You can save yourself a lot of work by doing so. Now this question does not say I can leave the answer in polar form. So if I go ahead and change that back now into rectangular form, a is equal to r times the cosine of theta, so that would be 1.41, or root 2. times the cosine of 225. And I get, in this case, negative 1.00 for A. And B also becomes negative 1.00. And that gets multiplied by J. So there is the second root in exponential form. Really, if you had used root 2, you'd get negative 1 minus J. It's exactly that. That's what it would become. And again, you could check that on your calculator by squaring that to make sure you end up with 2J, or 2I you will see on your calculator, okay? So there you go. We found the 2 square roots of 2J. Now, the next example is a little longer. So I think what I'm going to do is, I'm almost out of time here now on this video. I don't think I have time to do this example. So what I'll do is I'll do one more video, and on the second video I'll do this example. This is on page 26 once again. Make sure you watch the second video in this series. Thank you.